trying to figure out this semester. All right, so basically we're picking up where we left off in that course we had last semester on number theory, but you know, for the most part we're using Dummett and Foote, you know, the Abstract Algebra 3rd edition, and we're starting in Chapter 13, which seems at first glance kind of absurd, right? But actually we'll come back and do stuff in Chapter 10 and 11 later. And essentially we've already covered section 13.1 and 13.2 in the previous course, but I'm just going to start at the start of Chapter 13 so we kind of have a complete discussion here, all right? So we're talking about field theory, right? In the sense of mathematics, field theory in physics is something really different. So we'll start by generically saying that F is a field. What that means is, what does that mean? It means it's a commutative ring with identity, right? Such that what? Such that every non-zero element has a multiplicative inverse, right? So F with an X up is going to be F with 0 removed. So that is the set of elements in the field which have multiplicative inverses, right? Next up, you can talk about the characteristic of the field, right? And it's either equal to a prime P if 1 plus 1 plus da-da-da plus 1 P-fold times, right, is equal to 0, then it's said to be characteristic P, and it's said to be characteristic 0 if 1 plus 1 plus da-da-da plus 1 is not equal to 0. Let's say that's n-fold for all n. So either the field has characteristic P or it has characteristic 0. P is a prime, all right? Those are your choices. And we remember we have some basic rules of arithmetic that you can build from the identity in the field, right? So he's using 1 sub f all the way up here, so like n times 1 sub f is equal to, 1 sub f plus 1 sub f plus 1 sub f n-fold times, right? And if that's for positive integers, right? If you have a negative integer, you can define n times 1 as adding the additive inverse of the identity minus n times. We know that stuff. And so we basically have these basic rules that is his equation 13.1, n times 1 plus m times 1 I'll suffer this 1 sub f here for just a minute more, is equal to n plus m times 1 sub f, right? That's one of the rules. And the other one, of course, is that if we take the product of n copies of 1 with m copies of 1, we get nm copies of 1, right? And these rules are defined for positive integers, but then naturally extended to all integers, all right? And essentially, these allow us to build the prime subfield of a given field, right? So like, given F, right, there exists let's say, I don't know, I need another. Does he have a name for it? I guess he doesn't have a particular notation for it, but there exists, let's say, f prime, a subset of f, where where we can build this f prime from, it's generated just by 1. Like adding 1 repeatedly gives you the integers, or it's either the integers or z mod p. And then if you look at the field of fractions over that, there's an isomorphic copy of that that has to be inside the field. And so that forms the prime subfield. The prime subfield. So this prime subfield, it has to be contained. The prime subfield is the field which is contained in any subfield of a given field, because every subfield of a field has to have 1 in it. And once you have 1, you get the integers and you get the field of fractions over the integers. And so the prime subfield either is z mod pz, or it's the rationals. So this is characteristic p. This is characteristic 0. So those are your choices for the prime subfield. All right. So he gives examples. He's like, both the rational numbers and the real numbers, both characteristic 0, and well, he also mentions the integral domain Z also has characteristic 0, right? We can talk about characteristic for a ring. We don't just have to talk about characteristic for a field, right? We know that. All right, let's see here. Another example of something with characteristic P would be if we look at polynomials. So I guess some notation here I should start to use. F sub P is his notation for Z mod PZ, which of course we've also denoted by Z sub P at various points, right? So I shouldn't say example, this is definition. So the finite field, right? With P elements, F sub P, that's just Z sub P, right? So, okay, great. And another example, there's many examples, of course, of rings that have characteristic P. Another example would be, he mentioned, which I think is worth mentioning, if we take polynomials, right? Polynomials over, with coefficients in the finite field of prime P. That's again a ring of characteristic P. However, this is an infinite set, right? In contrast, F sub P is a set with P elements, right? P minus 1 having inverse 0 is the only thing without an inverse. All right. So as I was saying, the prime subfield of the rationals and the real numbers is the rationals, right? And so this is polynomials, right? Polynomials in x over fp, we can say it that way, right? And then if you build the field of fractions for this, what do you get? What's the field of fractions over the polynomials? Well, that's the rational functions, right? So like so if we look at f sub p of x, this is the smallest field, right, which contains up to isomorphism both f sub p and x, an indeterminate. And so we explained last semester that is basically things of the form f of x over g of x, such that g of x is not equal to 0, and f of x comma g of x are polynomials over p, f sub p. So this is an infinite field of characteristic p. So that's kind of interesting. You have a finite characteristic, but an infinite field. And so it's an important example. That somebody asks you, what's an infinite field with characteristic p? Well, here's your example, right? And you can put p equal to 3 if it makes you feel better, you know. But the prime subfield of that is what? Mm. So subfield to have g of x equal to 1. It has to be a field, though.
Things prime in the rational numbers, mod that. Mod the prime rational.
So if we just took the constant rational function, just 1, okay, right? But it's 1 mod p, yeah, and then we build a field from that, we get fp. So
yeah, you can break it. You can always break up a field.
Yeah, so like whenever anybody asks you what the prime subfield is, like the answer is either the rational numbers or f sub p. Those are your choices. Okay, so moving along here. Definition. If you have a field f, a field k containing the subfield f, then k is said to be an extension field. If field k contains subfield f, then k is an extension field of f, right? And we draw a picture like this to illustrate this idea, this diagram. In this context, f is sometimes called the base field. So this is the base field. This guy, of course, is the extension field. So if k, and we also write this, we write k over f to mean, you know, k is extension of f. Right, so this is not a fraction, it is another, the notation for extension, okay? This is important because we're going to be using this notation a lot. All right, and so notice that this makes, if you think about this, right? So let's just stop and smell the roses here for a second. So if, let's see here, we have, you know, f is a subset of k, right? And if you have, you know, say x and y in k, and c1 and c2 in f, what can you tell me about, like, c1x plus c2y?
That number has to be in k.
Has to be in k again, right? So, in other words, arbitrary linear combinations over f linear combinations of k are in k again, right? So write that out, write that down. F linear combos of k elements are again in k. In other words, what we're observing is that k is in fact a vector space over f. So observe. K is vector space over F. And what I'm saying is we can think of multiplication by F scalars as, those are the scalars for the vector space. That's what I mean by that, right? And so, well, you know the deal with vector spaces. They're either finite dimensional or they're not, right? So if K is finite dimensional over F, then we have a definition for that. It's called the degree, right? So, the definition, the degree, or relative degree of K over F, right, is denoted K colon F, right? And it is equal to the dimension of F over K, equals dimension F sub K. Which is just a fancy notation for saying, if K is finite dimensional over F, you count the number of things in the basis for that, and that's its dimension. And I think Dummett and Foote also allows for the possibility of infinite dimension. Okay. Well, anyway, here what he says the extension is said to be finite if the dimension is finite. So it's a finite extension if the extension field is a finite dimensional vector space over the base field. Yeah. Okay. And so, why did we? What prompted this whole investigation? Well, you remember. So why? Why do we care? So, x squared plus 1 equal to 0, no solution, right? In R. But, as you know, if we extend by, if we look at the, R extended by the I, right, where I squared is minus 1, of course we know that that's the complex number system, right? And I squared plus 1 is equal to 0, so x equals to I solves x squared plus 1. So one of the x squared plus 1 equals 0, and so one of the fundamental questions here is, given a polynomial equation, right, can we find a field where that polynomial has a 0 in it, right? Is there an extension field which contains the root of p of x? So to formalize this concept, right, we need to talk about the homomorphism of fields and like, for example, this basically, to make sense of, like, you'd be like, well, this is a real polynomial. I can't plug I into it. I isn't a real number, Well, you have to understand, like, the evaluation homomorphism can put, it gives us a way to put other numbers into this, even though we're thinking of this as a real polynomial to start with, but the evaluation homomorphism allows us to evaluate a polynomial over the base field of an extension field at an element in the extension field. Okay. But I'm getting ahead here. Let me stick with the Dummett and Foote story here. So let's see here. So let's look at proposition 2. I wonder what proposition 1 was. I forgot to call it proposition 1. I think it was something about characteristics, but
Okay.
yeah. Proposition 2, let phi from f to f prime be a homomorphism of fields. What does that mean?
You preserve one for sure for the identity, and you gotta make sure that yeah, I'm pretty sure you just preserve one, and then it has to have another thing besides one that also preserves.
Right, yeah, I think that means, like you said, phi of 1 sub f equals 1 sub f prime, and phi of x plus y is phi of x plus phi of y, and phi of x times y is phi of x times phi of y, right? It preserves the addition and the multiplication of the rings. Every field's a ring, of course, and it takes 1 to 1. And homomorphism, so we don't know whether or not it's
Yeah, it doesn't have to be invertible.
yeah, it doesn't have to be invertible, it doesn't have to be a surge action. But actually, this we get to say, here's kind of the punchline, then phi is either identically 0 or injective. It's 1 to 1, it's injective, you know. So the image of phi is either 0 or isomorphic to f. So phi of f is either equal to 0 or phi of f is isomorphic to f prime. I need to check on my monitor, see if I can't remember. Yeah, oh yeah, blue shows up. This blackboard is amazing. You can use all the chalks in this thing. You know,
Oh, I'll try to get another room.
yeah. Well, hopefully we can requisition some for the other rooms. We'll see. I mean, I think we have money for it. It's just we gotta decide where to put them. All right, so.
Put them over. You know, the pull-up boards, pull-up and pull-down boards.
Mm-hmm. The pull.
You know, like the boards that you just like push up.
Oh yeah. That'd be cool. All right, China. So this is from, excuse me, this proposition actually was proved back in chapter 7. So, excuse me, when you have a field, what are the possible ideals of a field?
Prime that split the field up.
So what are the ideals of a field?
One and pretty much its primes, right?
I guess it depends on, well, either, so with an ideal, right, in a field, if it contains a non-zero element, right, then we can multiply that non-zero element by its inverse, which means that 1 is in the ideal.
Yeah.
So if the ideal is non-zero, it has 1 in it, which means it has everything.
Yeah.
So the ideals of a field, they contain a non-zero thing and they're everything, or they're just the 0 ideal. So your choice for an ideal in a field is either 0 or the whole thing, right? And if it's a homomorphism, the first isomorphism theorem says what? Also, remember the kernel of the homomorphism is ideal of f, right?
Yeah.
So first isomorphism theorem says f mod the kernel of phi is isomorphic to the image. So that's this proposition essentially, right? The kernel is an ideal of a field. So there's two choices. It's either 0 or the whole field. If the kernel is 0, then that means if the if the kernel is 0, then that means f mod 0, like f mod 0 is isomorphic to f, right? Which is isomorphic to then phi of f. So if the homomorphism is non-zero, then it must be that the kernel is 0.
Yeah. Would that mean it just has one element in the field?
No. I mean, this, let's see here. For example, we could do phi of like x equal to x, where phi is going from the real numbers to the complex numbers.
Okay.
So kernel of phi is no, what maps to 0?
Oh, what maps to 0?
Yeah, the kernel's added. It's an additive
Oh,
kernel.
Yeah, 0, anything that combination.
Right. So it's anything that maps to 0, right? But but if x maps to x, the only way that you get 0 is when you put in 0, right? I mean, the kernel's 0. So of course, phi of x equals to x is 1 to 1. And so what this says is that the image is a right. So like there is inside, I mean, we can draw a picture, right? Here's your number line. Here's your complex plane, right? And this mapping, what does it do? It takes the number line and it just lays it out like that. And so this over here is technically phi of r, which is a subset of the complex number system. So it's kind of silly, but you could say, well, technically the real numbers inside the complex numbers are different than the real numbers because you can add I to them. But this is a somewhat useless distinction. And anyway, the point is that there exists an isomorphic copy of the reals inside here. And so for almost always, we just consider that isomorphic copy to be the real numbers in the interest of not going crazy with uninteresting and silly isomorphisms. But
Oh, okay. So if the kernel had more than just 0 in it, you'd find more than just that copy of R.
yeah, well, the only thing, this is what the theorem says, is the only mapping I can get besides this in this situation is the only other mapping like this would just be phi of x is equal to 0 for all x, which is just the 0 map. So then the image is just 0, which of course is not a field. Yeah. Then Theorem 3, one of my favorite theorems. Theorem 3 is let F be a field P of X polynomial over the field, which is irreducible. Right, irreducible. Then there exists K over F containing, well, excuse me, let me say it carefully here. Then there exists K containing an isomorphic copy of F. P of x has a root. So he says identifying f with this isomorphic copy shows that there exists an extension of f in which P of x has a root.
Yeah.
It is a slight abuse because it's not, it's,
I just think about the reals to the complex, like the complex being the extension field.
right, so that,
You have an irreducible polynomial, just extension field it out, and it has to have an isomorphic between the base
Right.
and the extension. So
right.
that,
Yeah, so let's look at the proof, and I'll show you what the subtle, there's a subtle point in here that we eventually want to gloss over. Like, I think it's already sort of been like glossed over in your mind because we've done it before. But at the base of things, there is a distinction between the f and the f prime, which if you're not aware of, can get you. But what you're saying is not wrong. So it's what we take away from this discussion. So proof, we let k be the polynomials over f mod the ideal generated by P of x, right? He says, since by assumption P of x isn't irreducible, we know that, and also he doesn't use this notation. In Dummett and Foote, the ideal generated by P of x is just noted like this. Okay, so here, P of x is by definition P of x times f of x, such that f of x is an f of x. Is that enough f of x's for you? There you go. So the ideal, but because P of x is irreducible, meaning what? It has no non-trivial reduction, right? Any factoring of P of x has to include a unit. So that implies then that this is maximal ideal. And by the other theorem we proved last time, thus f of x mod this maximal ideal is a field, yeah. So we know that. It's a field. And then what he says, and this maybe we didn't talk about, is that the canonical projection pi of f of x to the quotient restricted well, let me write the words down and then we'll try to dissect them, okay? The canonical projection pi of f of x to the quotient restricted to f, which is a subset of f of x, right? Gives a homomorphism. Phi. All right. So phi is equal to pi restricted to f. That is a mapping from f, of course, to k. And he points out which is not identically 0 since it maps 1 to 1. Hence, by the proposition above, phi of f is isomorphic to is isomorphic to F. An isomorphic copy of F is contained in K. So let me try to unpack this a little bit. What is this? Because some of this language is new to us. What is the canonical projection?
Is that the image of f of x onto f of x, or the mod of it, the extension field? I don't know what I'm saying.
So yeah, like let's see. Here's the formula for it. Pi of, let's say, g of x, right, is equal to g of x plus the ideal generated by p of x.
Okay. Well,
Sometimes this is called the quotient map.
yeah, but yeah, my understanding is that if you take a mapping pi and and essentially, like, if you try to map things from f of x from f to k, if you put everything in f and through that mapping, you'll get f back.
Well, that's what we want.
But the thing is, like, you're restricting it to f over f of x.
I mean, the fussy thing here is that the image of this map over here in K, it's things like so in here you've got a constant, right? And you're mapping it to something like a constant plus
Yeah, the ideal.
plus that, right? So they're different objects, right? But the point is that, okay, so why is it that the set of such things in K forms an isomorphic copy of F?
It's just, I just think about it like kind of like a transformation in the field.
Uh-huh.
That's all I think about. It's like, if you have a mapping that takes x to x plus 3, it's just a transformation, just like this would be a transformation, just it's by the ideal.
Right. I mean, I think you're right. If we just look at those kinds of things, it's clear that they have, like we looked at it last term in terms of, well, you can add them together, you can multiply them, and if it's non-zero, it has a multiplicative inverse, so it's a field. And also, it's clearly isomorphic to the other one, right? But the argument here is a little bit different because we're using this proposition too. So the point here is that pi is a homomorphism. So when you take and map from a ring to the factor ring, just by mapping the representative to the corresponding coset, so representative g of x coset with representative g of x right here, that's a homomorphism. If you take a homomorphism and you restrict it to a subring, it's still a homomorphism. But of course, this subring is also a field. So now we have a mapping from a field to another ring, which is a homomorphism. And then, so there are two choices. But this is also a field, because we already argued it appears as a field. So you got two choices. Either this is identically zero, this map, or it's non-trivial, in which case the image of F has to be isomorphically embedded over here. So like we don't have to do those things that you were thinking through because we can use the mapping argument. That's you're not wrong. It's just like
we're using this to just show that you don't have to go through brute force it.
Right. And so that's one of the differences between, say, Dummett and Foote and some of the lower level algebra books, is Dummett and Foote will try to use mapping arguments when it can, when they're clear, like here. Whereas I didn't try to do that last semester, really, because it wasn't appropriate to that course. Now, it's got a little bit more here. So he introduces some notation. He says, if x bar is pi of x, right? So in this notation, this would have been like g of x bar, right? So x is, here I'm using x as the element, there g of x is x, So if x bar is pi of x, all right?
And that bar is stating that it's with the ideal.
Yeah. All right, then what? Then P of x bar, right, is equal to, whoa. Hmm. All right, well, this is pretty sneaky. So he says P of x bar is P of x bar. But what he's arguing there, maybe I should unpack, because what we're really saying is P of, like, you know, the projection map of an element. Let's call it alpha for a second, right? I want to replace x with alpha, just so it's less, you know. Well, P is a polynomial, right? So this is something like Cn pi of alpha to the n plus dot 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 plus C1 plus C2 pi of alpha squared plus C1 pi of alpha plus C0, right? But the thing is, what is like pi of alpha squared if pi is a homomorphism? And really, that calculation is mission critical to this argument. Like, that is it. So because it's a homomorphism, the image to a power is the image of that power. Like, this is Cn pi of alpha to the n. C2 pi of alpha squared plus C1 pi of alpha plus C0. But then pi is a homomorphism, right? So, and what are these where are these c's coming from? Remember, the polynomial, it's a polynomial over f, right?
Yeah, and we're doing, it's like that, the vector space thing.
Right, so we can pull the, well, it's not just, I mean, to be totally pedantic, it's like this is, Cn is pi, it's pi of Cn. This is pi of C2. This is pi of C1. That's pi of C0. Sorry, I'm getting kind of small. Like, these coefficients are equal to that.
Oh, your note over here makes sense. That note.
Right?
Yeah.
That's part of it. But the other part is because pi is the projection, so like...
You can switch to CNs?
Yeah. I mean...
Oh, wait, no, it's already an F, so if you run it through pi, it's going to give you the thing back. Yeah.
Yeah, I mean... So...
Because to get Cn, you have to put Cn through pi, right?
Yeah, I mean, technically, I really should be writing... Remember, pi is a mapping from... Yes, this is fine, because... Well, anyway, let me stop writing and just get to the point here. Maybe that's anyway, I'm not sure how helpful that comment I just made is. Excuse me. Anyway, so this is pi of Cn alpha to the n, C2 alpha squared plus C1 alpha plus C0, which of course is, you know, excuse me, pi of P of alpha. So when he says P of x bar is equal to P of x bar, he's doing all that.
Yeah. No, but I get it, yeah.
And then he's like, well, remember that this is just notation for what? P of x plus the ideal generated by P of x, right?
Yeah.
Which is, of course, 0. Right? Or he just says it's 0 in, you know, f of x mod P of x. All right. So k indeed does indeed contain the root of the polynomial P of x, and k is an extension of f which has polynomial in which polynomial P of x has a root. All right. So, excuse me. Our goal in this, arc of the course is to study this idea of extension field, right? And what we'd like to do is find an extension field which contains, not just one of the roots of the polynomial, but all of the roots of the polynomial. So, like, that kind of extension field is called a splitting field. So, definition. So for P of x, polynomial over f, right? The k extension field k over f such that k contains all roots of P of x, if you like, all zeros. Called a splitting field. So you already know, if we have, well, let's go back to our most beloved example, x squared plus 1, right? So if we take, this is a real polynomial. Of course, we could also look at it as irrational if you like. Then, tell you what, I'll make it rational to make it a little bit different, a little bit more funky. All right, then Q adjoin I, which is things of the form A plus BI, A and B are rational numbers, has P of I equal to 0 and P of minus I equal to 0. And, of course, P of x is equal to x plus I, or rather x minus I times x plus I, right? So that's why it's called a splitting field. It allows us to split the polynomial into a product of linear factors possibly repeating. That's why it's called a splitting field. So, yeah.
But it's only for that polynomial specifically. Actually, no, it should be for all of them, right?
Well, that's an interesting. So that's the kind of question that we're going to be asking as we go forward in here, and your homework is about, like, if we had say q of x equal to x squared plus 2, it's not split. Over Q adjoin I, right? This one, of course, you need right, elementary algebra, we know that. So this is actually split over Q adjoin I root 2.
Yeah.
Or if you like,
So splitting extension fields don't necessarily have to split all cases. They just have to split a particular.
it's with respect to a given polynomial. Yeah. I mean, there is also that concept of what is the, like, overarching field which splits all possible polynomials of a given field. There is that as well. Forget the name of that thing, but it does have a name. He does discuss that in here.
No, it's just I was trying to think of the complex numbers, and I was like, well, complex, they don't just split.
That's true.
One, they split almost most.
That's right. That's part of the reason I did Q is because that ruins it, you know. But you're right. If we had the real numbers and we split x squared plus 1, you know, the harvest is bountiful. We've also split every other irreducible quadratic. And the rest of the quadratics could already be reduced. They're already split. Okay, so where was I? Theorem 4. What's it say? Theorem 4, we have an irreducible polynomial p of x of degree n. And so p of x and f of x, irreducible, degree of p of x equals to n, right? Then k equals to f of x mod the ideal generated by p of x, right? Has, I'll just write it this way, it's the span, it's the f span of 1 theta, theta squared, theta to the n minus 1. And more than that, I mean, this is a basis, all right? Linearly independent over f. So in other words, 1 through theta to the n minus 1 forms a basis. And what do we mean by theta? Well, theta is equal to x plus p of x, right? So we used alpha a lot in the last course for that one, but it's this result again. And so to be even more explicit about this result, that means that k can be written, right, like c0 plus c1 theta, plus cn theta to the n minus 1, such that the constants are from the field. So as we, k is an n-dimensional vector space over f with basis 1 through theta, theta squared, all the way up to theta to the n minus 1. Right. And I'll let you read the proof in there. I'm not going to do it again, but the proof is nice. It's about a page. And, he has a complete and careful proof of that in general right there.
Which chapter?
This is page 513 to 514 in the third edition of Dumb and Foot. And he has a corollary to that theorem. Let's see here. So he, in the proof of Theorem 4, he proves the linear independence of them, and he also shows that they must form a basis because there are n of them, and we also, here's another argument that the degree, like the dimension of k as a vector space over f is n. So, all right, corollary 5. says this. It says, let K be as in Theorem 4. You know. So what are we looking at here? Essentially, you know, you could write it this way. Well, fine, I won't. C0 plus C1 theta, Cn theta to the n minus 1, such that the C sub I are an F. All right, so K be like that again. And let A sub theta, B sub theta be elements of K. So here he means like this would be like a representative A of theta, right? So he's saying like A of theta and B of theta are two such things, right? Well, so there are two polynomials of degree less than n in theta. And then he says addition in K is defined by the usual polynomial addition, and multiplication in K is defined by A of theta times B of theta is equal to R of theta. So he said, first of all, he says addition, add as usual, you know, A of theta plus B of theta. In other words, he's saying if you have two of these things, you just add their coefficients, right? Add their coefficients. And multiplication, A of theta times B of theta, he says it's just equal to R of theta, where, what's this R of theta? Where R is the polynomial, all right? In fact, it's the remainder of degree less than n obtained after dividing polynomial A of x, B of x by P of x. So R of x is polynomial remainder for A of x, P of x, B of x rather, divided by P of x. So because this has degree n, right? This has degree n. It must be that this has degree less than n. So this claim up here makes sense. You know, we're saying it's a polynomial of degree less than n in theta, which is a typical element of K, you know. So this observation is useful if you're trying to prove some kind of general thing about multiplication of polynomials in one of these quotient rings, you know. Let's see here. He says, by the results proved above, the definition of addition and multiplication on polynomials degree less than n in theta make K into a field, so one can divide non-zero elements as well. He says, which is not so immediately obvious from the definitions of the operations. Fair enough. And then, like I talked about last time, it's important that P of x is irreducible. If you try to go through this construction when P of x is not irreducible, you won't get a field. You'll get other things.
Is that because you can split up like the cosets, or cosets is kind of like that?
It's because if it's not irreducible, it's not a maximal ideal. So when we mod by something that's not maximal, we don't get a field. But what you will get, like, typically you get like direct product of fields because of the examples I look at. But so his example 1 is just take real polynomials, mod x squared plus 1, and he just goes through the steps of the complex number construction. His second example is the one I just gave over here. All right, good. His third example is to take the field of rational numbers and look at x squared minus 2. Let's look at that one. Example 3 in his